Welcome. In this video, I will find the derivative of a composite function. It's not going to be any composite function. It's going to be the composition of a parametric curve and a function of two variables. All right? The graph of a function of two variables is a three-dimensional surface. All right? So I'm going to take a parameter, some kind of number. I'm going to associate it to a vector in the plane. I'm going to associate to this vector the height over the plane on the surface. And in this sense, I'm associating this parameter to this height. So this is just a completely normal one variable function. All right? And an application of this could be that this could actually just be representing the trip, the height of a person traversing some kind of landscape. Right? So at any time, this function would tell me how high above the mean sea level are you, for example. All right. And the derivative represents how annoying this trip is. Right? How steep is the slope? And also, it also uses the speed that you're traveling at. I'm going to get back to that, okay? I'm going to take the derivative by first principles. So I'm going to use the secant slope, tangent slope type argument, right? So we have I have the so-called three-step rule where I first I take the rise, the difference in function values at 2 points. So that's going to be f of t plus h minus f of t. All right? So that's the rise of this function. So there's the difference in heights at 2 points along this curve. All right? I can write this as g, where g is my function of two variables. That's the surface. After I take some kind of parametric curve on my parameter t. Right? So I have the outer function g, which is a function of two variables, and I have this inner function s, which is the parametric curve. All right. Now I'm going to take, I'm going to split s into its coordinate functions, which I'm going to call x and y. All right. So this is the same thing as g of x of t plus h, comma y the same. And then I'm going to subtract that little thing over there. Now I'm going to do two tricks. I'm going to introduce a new variable, and I'm going to be adding and subtracting and rewriting. Right? So the first step here is I'm going to introduce the variable kx, where kx is the difference in x values here and here. Okay, so that's going to be x th minus x of t. All right? So if I use that here, what I get is I get g of x of t plus kx. If I isolate this term in this definition here, I add this to the other side, and I get this is equal to x of t plus k of x, which is exactly what this is. Beautiful. I'm not going to touch the second variable here for now, but I am going to introduce a new term. I'm going to subtract g of x of t plus h. So kind of like the mix, like the halfway step between this and this. I changed one of these to this, but the other one stays the same. Okay, I've subtracted this, and then in theory I have to add the same thing here, and then I subtract this thing over here. Right. This thing I will save for now. That's why I kind of raised it, because I don't want to work with this right now. This is going to be, the argument involving this is going to be completely analogous to this. So I'm just going to focus on this term, and I made sure that I had some space here so I can actually use this dead space over here. Because what I want to do now is, I have found the, I change this, I found the change in y is this. So this is the rise. Now I actually want to divide by the run, and then I get the secant slope, right? So rise over run, and the run is, as usual, defined as h, all right? So now I'm going to divide by h, but I'm going to do it in a slightly weird way, all right? I'm going to make this fraction here, but I'm not going to divide by h here. I'm going to make a second fraction where the h goes. Okay? Cool. So I've divided by h now. Okay, so what do I want to have here and here? Well, here I'm going to write kx. And the motivation, I hope, makes sense now that I explain it, is that I want these two to match. What I'm actually constructing here is the secant in the x-coordinate up here. So I have a difference in the x-coordinates here, and then I divide by that difference, while the y-coordinate is kept constant. I divide by this thing here, but if I don't want to change this expression, I can't just divide by some unknown number factor. I have to multiply by the same thing, so they cancel. For the second one, I'm going to write this in a slightly weird way. It's not weird, it's just the definition of k, but I'm going to write it in two different ways, but it's the same thing, right? All right, so what happens here? Well, like I just mentioned, this was step 2 in the 3-step rule. Now I'm going to do the third step, and I'm going to let h approach 0. And that means that this whole thing approaches, well, this is the secant in the x-coordinate. So this is actually just the partial derivative with respect to x of this thing. That's the first fraction, this large ugly fraction, and then the second fraction is the secant slope in the x-coordinate function, all the way down. All right? So this is just x prime in t. Wonderful. If you look up here, I can do a completely analogous argument with the y's. All right? I divide by some ky. I rewrite this first thing here in this exact same way, and then I do this fraction, this fraction thing again, and I end up with the exact same thing, where I just swap out x and y. All right. And what is this beautiful little thing? Well, this is the exact same thing as the gradient of g at s multiplied by the derivative of s. All right, and this is the scalar product, I should say, because this is a vector and this is also a vector, so we're taking the scalar product. To those that recognize this, this is actually completely analogous to the chain rule for normal one-dimensional functions. We take the outer function, we take its derivative, represented by the gradient here, and we take the product, scalar product, with the inner function derivative. Beautiful. This is just a specific case of a very broad general rule for vector functions, where this becomes something more, these become matrices and stuff like that, but you'll hear more about that at university. All right. I mentioned earlier that this actually represents the how annoying the trip for the person on the landscape is. And that's because what this thing is, this is exactly the same as the directional derivative in this direction. Yes. So this is the directional derivative of g in the direction of t prime, s prime, sorry, at s, multiplied by the length of s prime. All right? So this number is the slope in the direction of motion, in the direction of where I'm moving, multiplied by my speed. All right. So if the slope is high, this is going to be annoying, and if I'm running, it's going to be annoying. If the slope is 0, however, then running feels pretty comfortable usually. If the speed is 0, then the slope doesn't really matter within reason, right? So if I'm standing still, it doesn't really usually matter how hard how slopey the landscape is, because I'm not moving. I'm not traversing that hill, right? So so a generalization of a previous result that I personally find really beautiful, and the argument is pretty well rounded. All right. If you have any questions or comments, leave them in the comments.